All right, so let's do an example. Let's find some equations for the line through the points 3, minus 2, 1, and 0, 2, 2. It doesn't matter which of these 2 points we use as our sort of fixed point, and which order we sort of use them to figure out the vector that describes the direction of the line. So why don't we just use this point, 3, negative 2, and 1. And so that means that x0 is 3, y0 is negative 2, and z0 is equal to 1. And then to figure out our vector that is parallel to the line, well, the displacement vector from P to Q should be parallel to the line because it's a vector that we can represent as lying right on the line. So we can take v equal to the vector with components 0 minus 3, negative 2, or 2 minus negative 2, and 2 minus 1. And that gives us negative 3, 4, 1. All right, so first, why don't we write down parametric equations. So we have x is equal to x0, which is 3, plus a, which is negative 3 times t. Y is equal to y0, which is negative 2, plus b, which is 4 times t. And z is equal to 1, z0, which is 1, plus c times t, and c is equal to 1, so great. All right, so this is a set of parametric equations. 3 minus 3t is x, y is negative 2 plus 4t, and z is 1 plus t. Now let's convert these over to let's convert them to symmetric equations. That's going to be useful for part B. So that means that we're going to solve each of these for t. So, and there's a straightforward way of doing this. For x, it's x minus x0, which is 3, divided by a, which is negative 3. This is equal to y minus y0, which is negative 2, so that's y plus 2, over b, which is 4. And that's equal to z minus z0, which is 1, over c, which is 1. So these are symmetric equations. Now we can use this to figure out part B. So this is part A, great. Let's do part B. For part B, we know that the xy plane is where z is equal to 0. So we've got that, great. Now let's plug that into here and figure out what that means over here. So for example, x minus 3 over negative 3 is equal to, when I plug 0 into here, I have 0 minus 1 over 1, which is just negative 1. So x minus 3 is equal to 3, and x is equal to 6. And for y, I have y plus 2 over 4 is equal to negative 1. So y plus 2 is equal to negative 4, or y is equal to negative 6. So this tells me that the point of intersection with the xy plane is 6, negative 6, 0. You can, again, plug these into these equations, verify that it's true if you plug these coordinates into here. You could also ask which value of t gives this to you. So if z is equal to 0, then the t should be equal to negative 1. And then if you plug that into here and here, you get, okay, 6 and negative 6, great, it all works out. So let's explore this case from the last example a little bit further and more generally. So we had a line that was determined by 2 points, and let's generally say we've got a point P0 with coordinates x0, y0, z0, and a point P1 with coordinates x1, y1, z1. We don't have anything quite analogous to a slope formula, y1 minus y0 over x1 minus x0, but we do have similar looking sorts of equations. So in the last example, we took the displacement vector from P0 to P1 as our vector v that was parallel to the line. So if we take ABC being x1 minus x0, y1 minus y0, z1 minus z0, then our symmetric equations look like this. This is a, b, c. We get x minus x0 over x1 minus x0 is equal to y minus y0 over y1 minus y0, and that's equal to z minus z0 over z1 minus z0. This looks very much like an equation for slope. In two variables, you can come up with an equation for a line using just this equation right here. That's valid. So this is evocative of looking at a slope type formula. Another thing we can do is to look at a parametric equation, a vector equation. So if r is a general point or a position vector representing the general point on the line, x, y, z, then we know that the coordinates are given by x0 plus t times a, which is t x1 minus x0, and the same idea for the y and z coordinates. Again, it's y0 plus t times y1 minus y0, z0 plus t times z1 minus z0. Now, if we do a little bit of algebraic manipulation, if we distribute the t through, we get t x1 minus t x0. And then if we factor out an x0 from the x0 plus t times negative x0, we get 1 minus t x0 plus t x1. We get the same sort of looking thing for y and z. So we can break this up into two vectors, one which is 1 minus t x0, 1 minus t y0, 1 minus t z0, which is precisely 1 minus t times r0, where r0 is the position vector for p0. And then we have tx1, ty1, tz1, which is t times r1, where r1 is the position vector for p1. So that's really nice. R is equal to 1 minus t r0 plus t r1. Great. And we can parameterize a line segment from p0 to p1 by taking this equation right here and then just taking t between 0 and 1. All right, so here's question 2. Let's let p0 be the point 213 and p1 be the point 03, negative 1. I'd like to find parametric equations for A, the line between p0 and p1, B, the line segment between p0 and p1, C, the ray starting at p0 and going through p1, and D, the line segment between q and p1, where q is the midpoint of the segment p0, p1. Here's a hint. The same exact equations for x, y, and z in terms of t work for all four of these. Just adjust your range for t. These are pretty much just following along what we've already done, and these two are just asking you to extend the ideas a little bit. Let's do an example. Let's show that L1 and L2 are skew lines, which means they're not coplanar. And here L1 is given by this equation, 3 plus 2t, negative 1 plus 3t, and t minus 4t, so it's parametric. And L2 is given by these symmetric equations. So to be skew actually means two things. You're not parallel, and you don't intersect, because any two lines that lie in the same plane are either parallel or intersect. So first, let's check that they're not parallel. So L1 here has vector, let's call it, V1, with components 2, 3, negative 4. This represents the direction. If this is A, B, C for a line, then that's our vector. Whereas over here, L2 has A, B, and C equal to 2, 3, 4. These vectors are not in the same direction because the first two components are the same, but the last two are different. So they're most certainly not scalar multiples of each other. So they're not scalar multiples, and so they're not parallel. So next we're going to see if they intersect each other, and probably the easiest way to attack that is from using parametric equations. So let's write down a set of parametric equations for L2. We've gone this direction a couple of times. Let's go the other way. Let's see. So here, this is x minus x0, so I could put negative 2 plus 2t 2t, negative 1 plus 3t, and 3 plus 4t. In fact, you know, I'm going to introduce a different variable because s and t don't have to be equal to each other. All we're asking is there any place where L1 and L2 intersect each other? That doesn't mean that whatever parameter I've got here for L2 and whatever parameter I've got here for L1 have to be the same. They don't have to be the same value. I mean, a single line could have a number of different parameterizations, so with different values of t giving the same point. So what we have to do then is set up a system of equations. So what we end up with is 3 plus 2t is equal to negative 2 plus 2s. Negative 1 plus 3t is equal to negative 1 plus 3s. And then 3 plus 4s is equal to 2 minus 4t. Now this is 3 equations. I had t on the left side. Let me do that. This is 3 equations in 2 unknowns. And generally, this is overdetermined. You generally don't expect this to have solutions. But we have to check anyways. Now this one equation right here, I made things a little bit easy for us. You could go ahead and solve and see that this implies that t has to be equal to s. So that means that we really have the 2 following equations. We have 3 plus 2s is equal to negative 2 plus 2s. And the other one is 2 minus 4s is equal to 3 plus 4s. So let's solve for s here. And yeah, this is never true. Because if I subtract 2s from both sides, I get 3 is equal to negative 2. Not true. So they don't intersect. Great.